So the recording is now in progress. So starting from this moment, the lecture will be recorded. So please be accurate with your questions and claims. So it is enough to prove the locality of GZ A of Z and B of Z. So why they are local? Yes, so we know that Z minus W to some n, A of Z, B of Z, A of Z, B, W is 0. And we want to deduce that there is some number such that here we can put the derivative. Differentiate. So indeed, so we take n plus 1, take the derivative. So of course this is 0, right? However, if we differentiate here, the corresponding term will vanish. Absolutely, thank you. So if we differentiate this power, then we would get nth power, and this kills the commutator. So this equals to Z minus W to the n, Z, Z, A of Z, and B of W. Absolutely. Thank you. So we conclude that the number we have to take here is n plus. So in particular, we see that the Heisenberg vertex separated algebra is indeed a vertex separated algebra. Okay. Good. So now let us make the more general claim. Namely, this claim is called the reconstruction theorem. We put it in the full generality. So the reconstruction theorem so what does it say? It says the following. So suppose we have B is a vector space. And we have S, the countable set. Yes, because so we didn't check all the properties, but what we did, we checked that all such fields are local. We've checked it at some point, and actually, well, this is a simple computation. So if you compute H of Z, H of W, so this is the sum H m Z minus n minus 1, sum H m W minus m minus 1, and this is sum over n times Z minus n minus 1 W n minus 1, which is the derivative, double derivative of the delta function. Okay. And so this derivative would vanish if you multiply it by Z minus W squared. T is just the derivative. Okay.
So about T, so also what about the condition?
The axiom, actually not. So the axiom says that y of TAZ is dt y of AZ. Yeah, this is the main point. And so we have to define the operator T on the vector space, and this sends Hn to Hn plus 1. In principle, this has to be checked. So this is not a void claim. Yeah, so we have to T of T is the derivative of the polynomial ring defined by T of H minus N is H minus N minus 1, maybe times, I think times N. Let me check. By N minus 1. Yes. What is the formula? Just one second. So what is the correct formula for T? Did I write it correctly?
I can see that T should compute this y.
Yes, maybe this. Yeah, maybe this is also true, but the condition was indeed like this. So this we'll prove actually this part. It should be default. Okay. And in principle, this we better prove this. So yeah, so the commutator is minus. Huh? And T of vacuum is yes, and this still to be checked. Okay. So let's see what does the reconstruction theorem say. So we have a vector space, and S is a countable set, and we have number of vectors A alpha from S. So these are vectors from B. Okay, and so we are given the fields parameterized by S. Okay, such that all A alpha are pairwise equal. Like this. So so assume further that A alpha of Z applied to the vacuum is A alpha plus Z times something. Okay. And even more importantly, that the vectors A alpha 1 minus J1, A alpha. Yeah, maybe I should have said that this V contains vacuum. Yeah, so we are given a vector space V with the vacuum vector 0, and we are given a number of vectors, countable set of vectors, A alpha, and we are given fields corresponding to each vector. These fields satisfy several properties. So first of all, they are pairwise local. They start with A alpha being applied to the vacuum, and we take JK. Yes, maybe I should write for A alpha Z being the sum alpha J Z minus J minus 1. Okay. So these guys like 0 form the basis V for J1 less or equal than JK, and if Ji equals Ji plus 1, then A alpha I should be smaller than A alpha I plus 1 for some order on. Yes. So let's see how does it work. Yes. So what are our assumptions?
I'm sorry.
Yes.
Then A alpha 1 is what? If J1 is equal to Ji plus 1,
then A alpha I is less or equal to A alpha I plus 1. Yes. Oh, maybe I better.
so there is not.
Yes. Better countable set with an order for the order. So I will have an example in a minute, but let me first just state the general theorem. Once again, so what we are saying that we have a basis of our space V, and this basis, how does it look like? So we apply some components of our fields to the vacuum vector, and the components, they correspond to, they have upper indices and lower indices, and the lower indices should be non-decreasing. Well, the important thing is that if you have two guys being equal, then you need some order on S. So you don't want things like A alpha minus 1, A beta minus 1, and A beta minus 1, A alpha minus 1. So this number. coming together. Okay. So
And the J are they not pointed there?
they are, thank you, they are. So you see, this is similar to what we have in the Heisenberg case, where our countable set is just one element set. Okay. And this is exactly the situation for the one element set. But if we have a larger set, then somehow you need more detailed description for this basis. So the basis is very similar, but you have to, so you don't want the repetitions of this form. So kind of ordering on the letters of this. So, okay, and then you can guess that the theorem claims that the formula y of a alpha 1 minus g1, a alpha k minus k, but the vacuum z equals to 1 over j1 minus 1 factorial, jk minus 1 factorial, z j1 a alpha 1 of z, dz jk a alpha k z defines the structure of vertex squared algebra on so this is the theorem. It actually looks complicated, however, not too much to prove here. So for the proof, we use the Dong's lemma. Yes, because we've seen that the derivatives of two local fields, they are local as well. Yes, so we see that the Dong lemma takes care of the locality property. Property of our fields. Okay. So what else do we need to prove? If we really need to prove something. Yes, that's a good point. So what is T here? So how to define our T? Yes, so if we take T with A alpha minus J, so this should be what? Right. T vacuum is. Okay, so therefore you can define T on any element of this form. Okay. This gives you the operator T. Okay, so maybe we'll get back there if we have some concrete example in mind. So let's let's formulate this example. But first of all, let me ask you the following. So please raise your hand if you've seen affine smooth Lie algebras somewhere, someday. Okay. And people in Zoom, could you please tell us if you've seen affine smooth Lie algebras somewhere, someday?
Я видела.
No answer? One, two. Are there still 6 people there? Approximately. 5.5. 4.5, including yourself or not? Oops. So yes, indeed, this is 4.5. Oh, okay. Then anyway, let me give you the main conditions. So let G be a simple Lie algebra. So you can actually think of G being SL2. Well, but it doesn't matter. Any simple Lie algebra would work, but so SL2 is enough for the constraints. And so we consider G tensor C inverse with the bracket A t to the n, B t to the m equals AB t to n plus m. So A, B are elements from G. So I sometimes put this tensor product sign here, but sometimes we omit it. So for notation, so A tensor t to the n is A t to the n. Sometimes it's also denoted by an. Okay. That's just a notation. Okay. And this algebra, which is called the loop algebra, well, it's a nice object, but one important nice feature of it is that that you can consider the central extension. So namely, the algebra G hat is G tensor C of dt inverse plus C times K, where K is central. So it means that K commutes with any element from this algebra, such that the new bracket A t to the n, B t to the m is A, B, T, n plus m, like this, plus delta n plus m 0, and then n, and then the central element K, and the last thing is the killing form evaluated at our two vectors and. Okay. So this is the formula for the central extension, for the one-dimensional central extension of the loop algebra. And well, indeed, one can check that this commutator is well defined. So I mean, satisfy the Jacobi identity. For that, the killing form property is used. Okay. So this is the algebra, but in order to define the vertex separated algebra, we need a vector space, yes, attached to such an algebra. And yes, maybe also one more thing to say, that this algebra has a Cartan subalgebra H affine, which is H tensor 1 plus 6 to the K. So this, for example, for SL2, this H is just the one-dimensional Cartan subalgebra for SL2, and for SLN, these are diagonal matrices, just a standard thing. And what we need is the sometimes what is called a parabolic Fermat module. Vk, where k is a complex number. So does anyone know what's that? What is the parabolic? Yeah.
For example, but you say that induced model from
Yes.
the model for
So first of all, from where to where? Yes.
yes from
G. T. Yes, and this. Maybe I write here full details. Yes, and of what?
of representation of
Well, if you consider the Fermat module, so it's just the one dimension. So if the zero modes, they act trivial. So parabolic means that this vector is vacuum in the sense that the constant G acts just by zero. So the top component is just one-dimensional trivial. Yes. So k is just a number.
But
Yes. Yes. So ck maybe. Yes. So what is ck? Yes. By definition, this is the span of one vector vk. So one dimensional vector. and the g of t applied to vk. Maybe I should put here also c to capital K. Thank you. Yeah. And then this is 0, and k times vk is k. Okay. So we don't want to induce to this central extension. So the central extension, the action of the central extension is fixed. So nothing else is.
Если бы там было тоже могли бы это сделать, но это уже не будет.
Yes, it's not a Verma module. So the Verma module is usually where you kind of don't have the. Okay, anyway, so the parabolic Verma module is exactly this. It's parabolic because it's a Verma module corresponding to some parabolic subalgebra of the affine Kazimud-Lie algebra. Namely, the parabolic subalgebra is this one, so which kills. And actually, having the finite dimensional thing on the top level, it's not a Verma module construction, but it's rather the quotient of the Verma. But in principle, you can also do this. So how does it look like? So let us draw the picture. So you have this vk, which is a kind of top level, and then next you have g t inverse applied to this vk, and then the next level you have g t minus 2 applied to vk, and also another part which is g t minus 1, g t minus 1. So more precisely, so let us put that as a remark. So vk has a basis. Maybe let's fix some notation first. So let J1, Jn be a basis of G. Okay. So n is the dimension of G. So this is a basis of our Lie algebra, and then Vk has a basis formed by J alpha 1 minus 1, J alpha k minus nk applied to Vk with n1 equivalent nk, and if n1 equals and I equals ni plus 1, then alpha I is less or equal to alpha x. So can somebody comment why do we have such a basis?
negative basis.
Mhm. Uh-huh. It's okay. So it's a question to the audience. So do we need to discuss this in more details? Or the existence of such a basis is clear? You see, this is a kind of special case of this reconstruction theorem order or reconstruction theorem basis, which is kind of very similar. Yes, so we order, so our S, capital S, here is going to be exactly the set of basis vectors for the finite dimensional linear algebra. And the property of having such a basis is somehow, this is the special case of such a situation. Okay? Is fine? Okay. So then this parabolic Fermat module, as you can guess, so it has a canonical structure of a vertex separated algebra. So how do we define it? Of course, via the reconstruction theorem. So vertex separated algebra structure. So how do we define it? So we say that J alpha of Z is going to be the sum. J, yeah, you remember, yes, that J alpha with the lower index means J alpha tensor T to this. So the sum J alpha n Z to minus n minus 1. So this is the vertex separated algebra fields, the kind of generating fields. So yeah.
Conditions of the reconstruction theorem.
Say again?
We want to define
Yes,
conditions.
to verify. So we don't have to define them, but we have to check, yes, that they are satisfied. So let's put forward the following lemma, saying that J alpha of Z applied to the vacuum is J alpha. Yes, by the way,
I'm sorry.
yes.
Here S is 1.
S is from 1 to n. Yes. And we have to say what are the actually, it's maybe a bit fast. So let us define, we need the vectors A alpha. Okay, these have to be vectors from our vector space, right? And this we define to be J alpha minus 1 applied to Vk. Okay, so all these vectors, they sit here. Okay. So of course the vacuum vector is going to be the Vk, right? And well, we put y of a alpha z to be exactly j alpha, right? So this is the definition. Okay. And now the lemma says that a j alpha of z applied to the vacuum is a alpha plus z times something. And the second part says that j alpha of z are pairwise. Okay. So what about the first claim?
I'm sorry, do we assume that we proved reconciliation?
Yes. So let's see. What actually do we? What do we need to prove?
Aren't we exactly in the conditions of the reconciliation?
We are
So we prove that we have
not yet, because you see, the reconstruction theorem somehow contains some assumptions, and the assumptions are that the fields are local, and that if you the assumption. So actually, let's write, maybe underline the assumption. So this is the one assumption, and we have another assumption, and we have yet one. And these assumptions have to be checked. So for the last one, we decided that we know this, but for the other two, we better check. So first of all, is this clear? So please raise your hand if this is clear. Yeah, Irina, can you explain why? Yes.
we apply to the k, therefore exactly what will be alpha times z to the power of q.
Okay, but why don't we have the negative power system? Right. You're right. So we have this induced module, and it is induced from such a module. And as we've seen here by definition, G of t vk. Yes, so by definition. But we need to check the second thing. So let us compute what is j alpha of z, j beta of w. So again, by definition, this is the sum, j alpha m z minus n minus 1. Then the sum over m, j beta m, w minus m minus 1. So how do we compute it? So first of all, so there is the term corresponding to all pairs n and m, j alpha, j beta, here n plus m, z minus n minus 1, w minus m minus 1. And then we have an additional term, the sum over all n, k times j alpha j beta sum over n times z minus n minus 1 w n minus 1. So please have a look at this formula. Let me know. Say me if this formula is convincing. So we do have to discuss why. That's fine. Okay. So then tell me please why the fields are local.
First term looks like some nation functions quite like some, for example, if the main part where n plus m equals to some 0, you mean
Well, we can take n plus m equals whatever, say capital M. Okay. So then the first thing is sum. So we have j alpha j beta, the sum over n, z minus n minus 1, w to, so minus m is n minus m minus 1, correct?
Right, capital M on the
Thank you.
n minus 1 derivative.
Of what?
Of the function.
Is it?
Or
Well, it's almost a delta function. Yeah, so just actually, this is j alpha, j beta, m, and then I can put out w to minus m minus 1, then delta function z minus 1. Okay. That's right. Okay. So what is the conclusion? Yeah, so the conclusion is that z minus w squared, j alpha of z, j beta of w is correct. Well, by the very simple computations like this. Again, then we see that the reconstruction theorem applies, and we do have a vertex separated algebra structure on our vector space. So the conclusion. So the reconstruction theorem applies. And we are getting we are getting the VOA structure on V sub key. So for example, y of j alpha minus 1, z is, well, z is just j alpha. Otherwise, you have some derivatives, you have normal ordering, and so on. Okay. So any questions, comments? Yeah.
For example, we can take those.
So we need a killing form. So you see, what we used is the existence of the formula, yes, for the commutator. Say again? Yeah.
Looks like this, but it's one-dimensional.
Yes.
Simple.
Mhm.
So it's like we can generalize.
Well, if we have some formula, we need some formula for the commutator. Yeah, so you're right. So for this Heisenberg algebra, we take a one-dimensional space, H, tensor it with C of TT inverse and add CK. So this is one dimension. Okay. And you're right. So we have a formula, and this the construction is of the same spirit. Absolutely. Well, for example, it can be semi-simple. It's also fine. So yes, if you have. It's also fine. So if there's a notion of the well, high-dimensional Heisenberg algebra, where you still take this H tensor C TT inverse plus CK, but this H is not one-dimensional, but something, and we'll consider such examples later. And it's important, and this produces the so-called lattice vertex separated algebras, and this construction is nice as well. So further questions? Well, absolutely. So I mean, I didn't say this. Maybe I should have said this. That there is a kind of so the so if V is graded and A alpha of Z have some conformal dimension, so related to the degree of a length. Yes, then we are getting some graded one, vertex separated. And of course, you're right. So the degrees of this A alpha, they do not have to be 1. It can be whatever. So in this example of the Kac-Moody vertex separated algebra, So in this picture, all these guys, they live on the first level. But in principle, you can take anything. For example, there is an example of the Virasoro vertex operator algebra, which we probably will start with next time. So where there's one generating field and the corresponding vector sits on the second. And in principle here, the levels are unconditioned. So you can take whatever.
Question: how works our multiplication? Now we have to like take two monomials, just reorders them to get multiplication on the vector space. I think about
I'm very sorry. So may I answer just one question? Just one second.
normal ordered multiplication of operators space, vector space. Where we get the same monomials and then we reorder
What do you mean? So you want to take J alpha minus K, yes, and J beta minus M.
we have, for example, G alpha minus K on which acts on value. Minus M, which also acts on value. We have corresponding operators that we can take.
Yes, this is, we know what. Yes, so this is derivative K minus first derivative of j alpha z, right? This is the g m minus 1, j beta of z. Yes.
Their normal order.
Mhm.
And then I want to find vector representation such that its image equals
This is nothing but j alpha minus k, j beta minus m, provided that, well, it's in someone, just or vice versa.
okay. But we didn't define our map for any such monomial. We have for like coordinates.
Yes, yes. Otherwise, we have to rewrite. So because the commutator is something. So any further questions? This is not clear how, because you need a vacuum vector, and then you need generating fields. Yes, so the usual thermal module would look like, so we have a vector. Say for example, okay. So you have F here, and then you have your E T inverse, E T inverse, and so on. And what should be the field versus So this is the reason why we kind of kill this. So factorize by this part. Take instead ft.
constructing the modifiable structure because from the more Lemma models, and this effort will go from different.
Actually, I didn't get it. So.
Можем ли мы как-то решить проблему с F, добавить не один модуль, а несколько?
So you mean
И F будет быть между разными модулями.
well, so there are some extensions, but actually you need much more to say. It's not in this simple. So I don't know what should be exactly the picture, but it could be. I don't know. So any further questions? Okay. So if no questions, then see you next time. Bye.